This meeting is being recorded. Continue. Great. So as I warned you in my email, I don't know when I'm going to finish, but when we finish, we're going to have an hour break, and then we continue with our recitation class. Okay, I should start by screen sharing. Yeah. Share. Oops. Now we go to lecture notes. And at least for starters, as a warm-up, let's go through the lecture notes. There's some things I can just skim through, and some others I'll be proving step by step very carefully. Okay, so I believe it's page number 14. Come on, scroll. There's some background noise and it's not coming from my laptop. Can you hear it? In the loudspeakers. Okay. Okay, here we go. So remember we proved this lemma last time that allows us to conclude under which conditions we can commute the operation of taking the FP functor and the push out. These are these two conditions over here, the vertex injectivity condition and the one color condition. Niklas told me that he has an alternative proof, and I'm looking forward to his proof at the recitation class. Niklas, yes, you will do it?
Yes, indeed.
Perfect. And to be honest, I haven't read what you wrote, but when I noticed that there's something imprecise in my argument, I realized that it can be also done without these CIs. So I'm going to see if your idea is the same as mine. But let's keep it for the recitation class. And now we go beyond this lemma, beyond this proof. We'll discuss it later on, as we said. Remember, last time it wasn't during the lecture, but it was during the recitation class. I basically reminded you what a pullback is. And it's not a big deal because it's exactly the same thing as a push out. You just reverse all arrows. Literally, you just reverse all arrows. And you go from pullback to push out. So there is no point of lingering on at this definition. And then I explained to you that if you are in the category of sets and maps, then the pullback is simply the fiber product with the canonical structural maps of the pullback being the projections on the Cartesian components. Okay, so here it is in the category of sets. And then we argued quite extensively that when you enrich your category, so when you have some structure, but the structure is preserved by the maps, then in fact you are having a pullback in this enriched category. And we did it for unital semirings and for semirings, okay? So these are very elementary arguments. I'm not going to repeat any of this. And now we want to prove some pullback theorems. This is what we are driving at. And this is why we looked at this very important contravariant functor of all maps into a given set K. Here I chose this K to be non-empty and have one distinguished element, but in fact, the lemma which I proved in the recitation class is valid for any sets. The empty set is also fine. Then you just have a very funny image. You just have one object and one morphism, right? But everything works. Universal property, you see, when you have just one thing between everything, everything works very easily. So there's no reason to cast away the empty set. And that's something very important for you to remember, because it's used everywhere in mathematics, this pullback construction, what it means to have a pullback of a map. This is, I know it's confusing because the pullback is used in two different meanings. One meaning is that of a pullback diagram, the categorical pullback. Another one is was, for instance, very extensively used in differential geometry. Whenever you have a smooth map between manifolds, when you pull back the RAM forms, for instance, okay? And these are exactly the formulas. You push forward vector fields, but you pull back differential forms. And then I want you to pay attention now, because I changed the definition of the second functor. I changed it. Okay, so it's not as it was a week ago. Okay, here's the definition. So what did I change? Now so for starters, I said that my distinguished element is 0, not 1. And of course, I did it because I want somehow to mimic finitely supported functions. But what does it mean, finitely supported functions, when my counter domain is just a set, not the field, not the group? So what does it mean, finitely supported? So I have to declare one element to be 0. And when finitely supported means that when I take away this one distinguished element from my set K, then the preimage of the set that remains is finite. That's exactly finitely supported, okay? And that's different than what it was before. I don't remember, before you had that the preimage of 1 is finite or something like this, okay? But this is a much better definition, because it's in agreement of what we mean by finite support when this set happens to be a field or an abelian group, or anything that has a 0. Okay, and now you look that indeed, if you have a map from X to Y, which is finite to 1, the pullback is well defined, which means that if you apply F star to a map from Y to K, which has this property, then as a result, you'll obtain the map which also has this property. Okay, so we have to verify it. So I take this F circle F, and I take the preimage under this map of the set in question, which is K less this distinguished element, which I denoted by 0. But of course, it's not a real 0, it's just a distinguished element. But then this is a general rule of what it means to take the preimage of a composition of two maps. This is preimage of a preimage in the reversed order. And now, of course, it works, because the preimage under F is by assumption, by the definition of the set map superscript F, subscript F. This is a finite set. And when I have a finite to 1 map, then the preimage of a finite set is nothing but a finite union of finite sets. So it's a finite set. So the condition is satisfied, and all this is well defined. So I really have a functor. This is also a genuine contravariant functor. But I don't know, maybe I shouldn't do this spoiler, but I'm afraid I cannot resist it. So spoiler alert. I was completely convinced that this functor will work much in the same way as this functor without restriction, but it doesn't. It's just not true. I found out this night that in fact, when you take the category of sets, but with morphism being finite to 1, this category is not closed with respect to pushouts. It's just not closed with respect to pushouts. It's not true that pushouts always exist. Okay, so I didn't expect such an abstraction. So this is part of the fun of teaching this course. That I sit down to write a lecture for a given day, and I have no idea what it will be, because I have to find it out first. So yeah, I mean, it's not a big deal. It's relatively obvious, but a counterexample is a nice problem for a citation class to really find a counterexample to prove. Give me two finite to 1 maps that do not have a pushout in the category of finite to 1 maps. Okay, so that's actually a nice problem. I tried to prove that such a pushout exists, and when I realized it doesn't make sense, I can construct the counterexample. Yeah, but you know, when Y is an arbitrary set and you take all maps, then this is what we did in the recitation class. So I just wrote that the proof is an exercise, and we did it in detail, and I'm not going to repeat it. And this is, I think, the time now that I switch into writing on a whiteboard, because now I want to go slowly over this. This is just a recall of what we did last time, basically at the recitation class. And I had to do it because there are some changes, okay? And the changes over here in the definition of this functor, map F. Okay. Of course, this is not, I didn't change the definition of the functor to somehow remedy a problem, or it also did not create the problem. The problem is somewhere else. The problem is, as I told you, that the category of sets with finite one maps is not closed under pushouts. So it doesn't matter which functor I take. It's just not closed under pushouts. So it will not, if I have any restrictions of that sort, it will not work. Okay, so now let me switch to, I stop sharing the lecture notes and switch to whiteboard. Where's my whiteboard? Here it is. As usual, it takes a while to set it up. Oh, no, this is what I want to do. How do I maximize it? Yes, now it's maximized. Might put it over here. Okay, and I can write. So you see this choice of a set K, which is non-empty, has a Swedish element 0, was done with a number of two things in mind. One thing is that then you can replace it with a field, and then 0 is really the 0. But there's also another reason. You see, I can take K to be the two-element set 0, 1. Okay, so it satisfies all these assumptions. So when I do this, I can identify this functor of mapping into K with the contravariant functor of taking all subsets of a set. And I emphasize contravariant because when you say taking all subsets, you are still not, this is just telling what your objects are. How do you create objects? But you don't say what you do on morphisms. And when I say contravariant, I mean that I take preimages, okay? So I have a map from X to Y, and then I have a set of all subsets in X, a set of all subsets in Y, and to have a map from the set of all subsets in Y to the set of all subsets in X, I take the preimages, okay? So that's why it's important to emphasize which functor I have in mind. And in fact, this is the more important functor. It has nice properties. Remember, this is how we define topology, how we define continuity, right? If you want to say that your map is continuous and you have your topology given as a family of open sets, then you must have that this is just a property that this contravariant functor will map the topology in Y into the topology in X. That's just a continuity. And it has all the nice properties. Okay, and now let me make sure that the statement is correct and crystal clear. If I take the maps, let me denote 1 by alpha X, and it goes from a space of all maps from X to K. to the space of all subsets of X. And what do I take here? I take a function, a map, okay? And I assign to it the subset of X, which is the preimage of 1. Okay. And of course, this is an element in 2 to the power X. And now the inverse, well, it's also obvious, although it's more difficult to write down. So now I take a subset A, and I assign to the function fa, well, which is defined as follows: fa of X is equal to 1 for X in A, and is equal to 0 for X not in A. So this is just the characteristic function of the set A. And let me finish the sentence. So indeed, the maps are mutually inverse bijections. Yeah, I hope it's crystal clear. If I start with a map F, then my subset is F preimage of 1. So now when I compute what is F of F preimage of 1, well, it assigns to an X1 if X is in F preimage of 1, but X being in F preimage of 1 simply means that F of X is 1, and otherwise it's 0. So this is exactly the function F you have started with. Yeah. And now if you start with the set A and go to the map F of A, and then you map F of A to the subset F preimage of 1, well, that's exactly the set A. Okay, so this is totally obvious that these two maps are mutually inverse bijections. But we have to check another thing, which is important, sort of the naturality of this map. So we have to verify that for any map G from X to Y, we have the commutative diagram. On one hand side, I have the space of all maps from Y to K. Then I go by the pullback map, G star to the space of all maps from X to K. You remember the definition. Here we have this alpha Y map, which goes to the set of all subsets in Y. Now, here we have is the preimage construction. So we just take the preimages of the subsets of Y and we get subsets of X. So we land in 2 to the power X. And here we have, of course, alpha X. And this diagram is commutative, right? And again, it's obvious because if I take, I don't know, let me take some map capital F in here. So I have G star of F, and when I apply alpha X, but this is X not star, but this is alpha X applied to F composed with G. And let's see how alpha X is defined. Well, I just have to take the preimage of 1. So this is this is F circle G preimage of 1. So that's what you get up here. I mean down there at the bottom right corner. And if you do it the other way around, well, then alpha y of F, and I have to plug in city. Okay. which causes some noise. Is this noise very bothersome, or can you put up with it? It's okay. And now it's okay. So it's alpha y of f, and then this is G inverse of this. But alpha y of f is nothing but taking the preimage of 1. So this is G inverse of f inverse of 1. So you see these two things agree, right? Because why did I write of A? Should be, no, this should be 1. Right, because the map alpha x means that you map f to the preimage under f of 1. Yes, so sorry, this is a mistake. But you see, these two things are obviously equal. Yeah, because the preimage of a composition of maps is the composition of preimages in the reverse order. Okay, so I just verified for you that this diagram is indeed commutative, which means that these maps identifications of a two-functor, this is a so-called natural transformation. So this means that I can really identify these two functors. Okay, they are naturally isomorphic. This identification alpha respects the morphisms. Okay, so it translates pullbacks into preimages. Okay, so now with this in mind, now we can view the contravariant functor assigning to graphs unital semirings as the composition of two functors. One is the covariant path functor, so the functor of taking all finite paths in a graph. And the contravariant functor of taking all maps into my two-element set K. All right, so now I can write it like this. I go from E to FPE, that's the covariant part. Now I apply the second functor, so these are all maps from FPE into the two-element set K. But it's naturally identifiable. This is why I write the equality sign, not an isomorphism, with a set of all subsets in the set of all finite paths in E. And if you remember, this was by construction RE. Okay. And everything is fine with a morphism because that's exactly how it went. A graph homomorphism went to a map between paths, a set theoretical map with some properties. And then this goes to pullback, but pullback is identifiable with a pre-image, and this is exactly how we defined this functor on morphisms. Okay, this functor R is viewed as a contravariant functor. So now if you combine, so now we are ready to combine three things. So this is this lemma, which proves it's 171 in the notes. This is the lemma which proves under which assumptions the FP functor turns pushouts to pushouts. Okay, so FP pushout to pushout lemma. Then the second thing is the lemma which we proved in the recitation class about this functor of taking all maps, the contravariant functor of taking all maps into the set K is a contravariant functor turning pushouts into pullbacks. So let me call it map K pushout to pullback lemma. And the enrichment of fiber products discussion. Remember, we discussed that if we endow our sets with additional structure, for instance, the structure of unital semirings, and our maps will respect this structure, then the fiber product will be the pullback in this enriched category. Okay, so now when you combine these three things together, you have the following theorem. So finally, something substantial after all this ado. So my assumption is the following: let this diagram be the diagram in the category of graphs. So here this is a bit difficult to write, but this is a pair iota E0, comma iota E1. And this is a pair iota F0, comma iota F1. And this is from F. And here we go from, from G. And here's F0, F1, graph homomorphism. And here's G0, G1 graph homomorphism. So let this be a push-out diagram in the category of graphs. In the category of graphs and graph homomorphisms, so not path homomorphisms, but graph homomorphisms. But such that the assumptions of this push-out to push-out lemma are satisfied. So I have to write the one color condition, both F0 and G0 are injective. So this is vertex injectivity. And when I look at the end in the push-out graph of an edge X and happens to be equal to the beginning in the push-out graph of an edge Y, then this implies that either both X and Y are in the image of iota E1 of the set of edges in E, or they are both in the image of iota F1 of the edges in F. So the one color condition. And remember, there was no assumption for the second lemma, absolutely no assumption whatsoever. It always turns push-outs into pullbacks. So I don't have to add anything else. And now I can claim what I want to claim, that is this functor of taking the unital semi-ring associated with a graph commutes, I mean, it turns push-outs into pullbacks under these two conditions. So R of a push-out graph, PFG, is the same as the fiber product of semi-rings, RE over RG, RF, and to make it even nicer, the contravariant functor R transforms the above push-out diagram to the pullback diagram of that form. I have the fiber product RE over RG with RF mapping to RE mapping to RF, and here mapping to RG. Okay, and this is given by simply by the F inverse. Okay, have a morphism from G to E, so we can now take the preimage of the induced map F, and the same here, G inverse. Whereas these are the canonical projections, so pi, or just let me write pi E and pi F. But to be consistent in notation, and this is how I wrote it in the notes, it's pi RE, pi RF, but this is like a cascade of subscripts and it looks a bit ugly. Okay, so this is, do I finish the sentence? To the pullback diagram in the category of unital semirings. And as I mentioned, so here, F and G are the maps induced by F0, F1, and G0, G1, respectively. Okay, and that's the end of a theorem, and we actually proved it over. So we were preparing all these lemmas and proving all these lemmas, so that at the end of the day we can claim this theorem. And I think that this is very nice because we have absolutely natural situation in the category of graphs. We have no assumptions whatsoever to begin with. We see that this category is close to respect to pushouts. We can always construct the pushout graph. And then Niklas proved that this pushout graph is in fact the categorical pushout in the category of graphs and graph homomorphisms. And then we have just one abstraction with this covariant functor FP. We have to put two conditions. And then we have no obstructions in turning pushouts to pullbacks by the contravariant functor map into K, right? And that's the result. Now the story with the restricted maps is going to be more difficult because I need to add one more condition in order simply to have pushouts in the category of paths. Yeah, when I have category of sets, but I'll have sets my finite paths in a given graph. And here there is this problem with this finite one. Yeah. But this is actually important because that's precisely what is more relevant to path algebras. Remember that when you define path algebras, you take all finitely supported functions from FPE into your field K. So that's precisely the second functor which is being used. And I'm doing these lemmas for a reason, because I don't want to repeat these lemmas when proving the pullback theorem for path algebras. So roughly speaking, the pullback theorem for path algebras should have exactly the same assumptions, hypothesis, as the next pullback theorem for this restricted functor. Any questions thus far? Okay. Let's continue. Yeah, as I mentioned, the push out to pullback situation, the contravariant functor E. So let me just write in the situation with the contravariant functor E to REF is more complicated. Because pushouts don't always exist in the category of sets and finite to one maps. So we have to sweat a little bit more. And I think here comes the lemma of the day, because I think this is the most or the only non-trivial thing I want to prove to you today. That's the lemma which has no counterpart in this previous functor story. Okay, but here we have to do it. What do we have to assume about morphisms in this category of sets and finite to one maps, so that the pushout exists? I'm not saying that this is the optimal condition. I'm not saying that this is a necessary condition. I'm just saying it's sufficient. So if you have any ideas of how to improve it, well, without being monstrous, I'm all ears. Yeah? I'll be very happy to listen to your ideas. But the quickest way out, when I faced this strange wall, which I completely, or obstacle, which I completely didn't expect, that the push-out in general does not exist, so I have to assume something more. Well, what came to my mind was that what I should assume is that not only both of these maps that I take, of which I take the push-out, are finite to one, because that's my category, but I assume that at least one of them is injected. And well, there is a justification to it, because in fact, when you do, well, let me make this remark here. Additional, but this is just a remark. So for instance, when you have a push-out diagram, I don't know, for some nice spaces, topological spaces, maybe you can talk manifolds, some say compact Hausdorff spaces at least. And imagine that you have a push-out construction, okay? Then if at least one of his maps is injective, and this is an important assumption, at least one of his maps is injective, this induces a 6-term exact sequence in K theory. Let me see if I can remember it correctly. So the point is to calculate, so I should map somehow, define somehow these maps. Okay, and let me see if I can remember it correctly. I think I start from, okay, you don't have to understand what it is. It's a certain contravariant functor which maps, say, compact Hausdorff spaces to abelian groups. But this is a very, very important functor of studying vector bundles. And it solves so many difficult problems in mathematics. Okay, so I apply this functor and I apply it to, I want to understand this K0 group of a push out, but this is difficult. And here I go into K0 of a disjoint union, but this is just the direct sum of abelian groups. So K0 of X plus K0 of Y. And here I have a difference map into K0 of Z. So if you want, yeah, this is a contravariant functor. So when I apply it here, I will have maps going into the opposite direction. So let me just denote them as pullbacks. So this will be F pullback minus G pullback. Okay. And here we go with K1 of a push out. Here some difficult connecting homomorphism. Here again you have K1 of X plus K1 of Y. And here I have a difference map going into K1 of Z. So again, I take F star minus G star, but now for the second K functor, the odd one. And again, I have a difficult so-called Milnor connecting homomorphism. So that's a theorem. And it also works for sister algebras. So Jacek, don't panic. This goes fully quantum, fully non-commutative. I just wanted to talk about push-outs, but I can as well talk about pullbacks of sister algebras. So when I talk about pullbacks of sister algebras, say unital sister algebras, this pullback has to be one surjective. At least one of these maps has to be surjective. But at the level of spaces for commutative sister algebras, it means that one of these maps is injective. So that's not such a horrible assumption, because if you want to do some computations, having a pullback structure or push-out structure, then for push-outs, you better be one injective, and for pullbacks, you better be one surjective. Otherwise, such theorems, such Meyer-Vetoris, this is called Meyer-Vetoris 6-term exact sequence. In K theory. It wouldn't work without this assumption, okay? You really, really need it. And Michael Attia had some beautiful lectures explaining how to prove it, that you have a 6-term exact sequence for spaces. Okay, but this is just a remark. If you don't know K theory, maybe it doesn't tell you much, but you should just remember that there is some extremely important functor, and it has nice properties. This is, believe me, one of the basic computational tools. Your life without it would be very hard. It would be like life without electricity, or I don't know, smartphone, internet. It's one of the things that make life possible. And this commutative, this exact sequence, okay? But we need assumptions to get it. So that's why I'm not so scared to assume that one of the maps in my push out is injective, okay? So let me write it down, the full assumptions of a lemma. So let this be a push out diagram, Ix, Iy, f from z to x, g from z to y. Let it be a push out diagram. In the category of sets and maps. Now, if one of the maps f and g is injective, and the other one is finite to 1, then the above diagram is a push-out diagram in the category of sets and finite to 1 maps. Okay, so that's the lemma. Let me make it crystal clear so that we understand each other, so we're on the same page. I assume that this is a push-out diagram in the category of sets, where I have no restrictions on maps. Now, when I restrict my morphisms in such a way that one of them is injective, so it's obviously finite to 1, it's 1 to 1, and another one is finite to 1, then my input data is in this category I'm interested in, the category of sets and finite to 1 maps. And now the big question is the outcome again in this category. So what do we have to verify? We have to verify that these canonical maps, Ix and Iy, are also finite to 1. And then we have to verify that the map witnessing the universal property is a uniquely existing map, different for each case, is also finite to 1. So these are two things that are non-obvious. And I was really, really surprised when I constructed an example in which both of these maps, f and g, are 2 to 1, in fact. And these maps are not finite to 1, neither Ix nor Iy. So of course, the push-out exists, but not in this category I'm interested in, okay? All right, so let's go ahead and prove it. I don't know, has anybody known this? For me, it was a discovery of this night. I had no idea that we have such a fun effect. I thought that taking the restrictions of going to finite to 1 maps is completely benign. There is no trap. There's no caveat, but obviously there is. Luckily, the price that we are paying for it is acceptable for the reasons I explained. Okay, so let's prove it now. Just to focus attention, so assume without the loss of generality, W log without the loss of generality, that F is injective. This is a completely symmetric situation. Okay, and of course, when G is finite to 1. Now, but I claim that then the canonical maps of a push out so iota x going from x into the push out, and iota y going from y into the push out are also finite to 1. But that's not obvious, so I need to prove. Okay, indeed, if iota y of y1 is equal to iota y of y2, then, well, either simply y1 is equal to y2, or there exists a finite sequence, and this time Jacek, this is even, because I have to end up in the same space by assumption. So don't try to convince me that it doesn't have to be. Or there exists a sequence, well, finite sequence, I don't know, I call them Z1 to Z to N, which is in Z to power 2N, such that I have G of Z1 is equal Y1, and F of Z1 is equal X1, and so on and so forth, until we arrive at the situation where I have F of Z to N equal X to N, and G of Z to N equal to Y2. Okay, and let me explain it a little bit, because this is much easier done with a picture, which is horribly complicated in LaTeX. So that's why I did it in lecture notes. I just wrote it in words. But let us understand what's going on. We have Y1 and Y2. And we can ask when they are identified by this equivalence relation, which defines the push-out. Well, they might be beyond, Y1 might be beyond the image of these maps that define the push-out, F and G. Then simply we must have Y1 equal to Y2, right? We cannot make any identifications in the things which are beyond the image. Here's this map G, right? So one thing is that they are equal. Well, when they're equal, that's fine, when we are finite to 1. Yeah. The point is to show that if I have I of Iy of iota y of y1 equal to iota y of y2, then with a fixed y1, I have only finitely many y2s that satisfy it. Okay. So in the first case, that's just 1. Y2 must be equal to y1. There is no other choice. Okay. Otherwise, well, we use the definition of equivalence relation, defining the push out. And it's as follows. Here I have some Z1. So this is my sequence, right? I have my Z1 and it's mapped by G to Y1. Then I have an F and it mapped to X1. Here I can take Z2 and it's mapped by F to X1. And I continue like this. Here again, G. And here I don't know, Y, 1, 2. It's not squared, it's just 2. And so on and so forth. And finally, we arrive with G, which maps Z to N to Y2. Okay? But now please note, please remember that F is injective by assumption. Well, F is injective and I have F of Z1 is equal to F of Z2 because it's equal to X1. And sorry guys, but Z1 is equal to Z2. And when you continue like this, when you realize, aha, so then Z2 is equal to Z3. Sorry, Z3 is equal to Z4. I mean, here, yeah, I don't assume that G is injective, so I don't identify Z2 and Z3. But when I identify Z3 is equal to Z4, Z5 is equal to Z6, and so on and so forth until I have that Z to N minus 1 is equal to Z to N. Okay. But what does it mean? It means that all these Y's that I have in between, that sequence of Y's is constant. Right? Because look, Y1 is G of Z1, but Y12 is G of Z2, but Z1 is equal to Z2. So Y12 is equal to Y1, and so on and so forth, right? Because of these equalities, you see that the sequence of Y's is constant. Okay? So in fact, we proved more. We proved that iota Y is injective. But injective is finite to 1. Okay, is this reasoning clear? Okay, Jacek agrees, so we move on. But now let me write it down. This was a picture, if you want, so that you can better understand what's going on. But now I want to write it as an English sentence. So in the letter case, which is, yeah, so this is the first case when I simply have, wait a second. When I simply have Y1 equal to Y2, in the letter case, which means that when there exists such a sequence, from the injectivity of F, we also conclude that Y1 is equal to Y2. So iota Y is injective. Okay. And now I have to use this zigzag argument again. This time it's going to be a little bit more subtle, but not much. Now I want to prove that iota X is finite to 1. So next, if iota X of X1 is equal to iota X of X2, then of course we have either X1 is equal to X2 and we are done, or, and now it's slightly more difficult, there exists a sequence, a finite sequence. Now let's call it, well, I still call it Z1 and so on, but of course we have different Z's. But now it's up to 2m. I mean, these are different sequences. Oops, these are not the integers. Sorry. Z to the power 2m. But this is a finite sequence such that and now we have a different starting point. So basically, I write the same thing I wrote here before, but now I switch the roles of f and g. So I have f of z1 is equal to x1 and g of z1 is equal to y1 dot 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 until we end with g of z to m being equal to y to m and f of z to m being equal to x2. Okay, and again, let me draw a picture for you. So this time we want to go from x1 to x2. So again, the idea is very simple. I fix x1 and I see how many other points can be identified with x1 via the map iota x. Okay. So if this x1 is beyond the image of f, that's it. Then any x2 identified with it must be just equal to it. Okay, so then it's just one element situation. But otherwise, we can use the definition of this equivalence relation, which effectively defines iota x, and write down this finite sequence. So I have a map f, which maps z1 to x1, then g maps z1 to y1, then I go to z2, and z2 is being mapped by g also to y1. Now I use f, and I go to say x12, whatever, and so on and so forth. Maybe let me shift this guy a bit further. And finally, I end up with this z to m, which is mapped by f to x2 and by g to say y to m. Okay, and now again, we are going to use the injectivity of f. So here's z3, and here's f again. And we know that as before, we have, because f is injective, I have z2 equals z3. I have z4 equal z5. So this time the equality is that z to n is equal to, well, maybe I should write it like this. Z to, well, the final one will be z to m equal to z to 2m minus 1. Okay. So these are my identifications, but the effect is exactly as before. I have only one y in my same sequence. Yeah.
Why do we have this last equality? Don't we have z to m minus 2? Equals zm minus 1.
Well, I have to end up with an f map to land in x. So that's why this sequence has to have even number of elements. Because here I alternate, it's f gg, then it's ff gg, and so on and so forth. And finally I end up with f. So I have an even number of Fs and even number of Gs and half as many Zs.
Z to M and Z to M minus 1 are mapped to the same element via G, not via F.
Yeah, it's okay. Yes. Sorry. You're right. You're right. Now I see your point. So yeah, because here you have this is by G. So what's the correct formula? I think that we have to go a little bit more down. So maybe the correct formula is Z to. Okay, so this is by G, but this will be by F. Okay, so Z to M minus 1 will be identified with Z to M. Okay, it should be minus 2 here. Yeah, thank you. Yes, of course. Yes. Yep, but the effect is still the same. All these Y's are constant. They cannot be anything else because I have my Y1 is equal to G of Z2, but Z2 is equal to Z3, and my Y1 3 or whatever this another Y which appears here, that's the image of the same Z. So that's by the same map. So it's equal to Y1. Okay, so we can denote all these Yi's just equal to Y. And this Y is uniquely determined because F is injective. F is injective, so I have that Y1, which is Y. So Y is equal to Y1, but this is equal G of Z1. But Z1 is simply, if you want, F inverse of X1. So once I fix my X1, I fix my Y. Okay. But what now I can conclude that all Z's for all I running from 1 to M, I can conclude that Zi is in the preimage of Y under G, sorry. Right, because each and every of these Z's is mapped under G to one and the same Y. But remember, G is by assumption finite to 1. So there are finitely many different Z's. Okay, so whenever I build such a sequence to witness the equivalence relation between X1 and X2, so that they're identified by iota X, well, I have to write such a zigzag. But when I write such a zigzag, my Y is necessarily fixed by the injectivity of F, and therefore all the Z's which appear in the sequence are in the preimage of my fixed Y. But G is finite to 1, so there are finitely many of such Z's. So no matter how long or how many sequences I write, I can have only finitely many outcomes. Because X2 must be, if you want X2, must belong to the image under F of a preimage under G. And this is a finite set. Okay, so this proves that iota of X is finite to 1. Okay, good. So this is, explaining it by hands waving. I mean, that's how it goes. There's not a big deal here. Now let me try to write it a bit more formally. So it follows. Any questions, by the way? Because since I don't see you guys, when Jacek and Anya are nodding, I think that everybody is nodding. But please, if you have any questions whatsoever, ask anytime. Okay, so it follows from the injectivity of F that all yi's are equal to G of Z1, where Z1 is uniquely determined by the equality F. Where is this equality? Is uniquely determined by X1. Right, because we have F of Z1 is equal to X1. So you can denote all of them by Y, right? So we can denote all of them by Y. So consequently, all the i's in such a sequence belong to the preimage under G of Y, which is a finite set by assumption. Hence, as any element x2 such that iota of x1 is equal to iota of x2, either equals to x1, in which case we're immediately done, or belongs to the finite set which is F of G inverse of Y. Right, this is what we argued for before. All the z's must be in the preimage of Y and the G, and all x's that are given by these equivalent relations that can be identified with x1 via iota x must be images under F of elements from this finite set. Okay. So as we have such a situation, we conclude that the map iota x is finite to 1 as desired. Okay, now we just have to take care of the universal property, which is much easier. So tell me if you have any questions to this argument. This is the most interesting part, in my opinion, of this argument. No questions? Okay. So the final step of the proof, universal property. So finally, if Jx, which is a map from x to some q, and Jy, which is a map from y to some q, are finite to one maps, such that they equalize f and g. So Jx composed with f is the same as Jy composed with g. Then the universal property map H from P to Q is also finite to one. That's what we have to prove. Well, indeed, suppose the contrary. Suppose that the set preimage under H of Q is infinite for some Q in Q. Okay. Then, because iota of x and iota of y cover everything, so if you want SP equals to the union of iota of x with iota of y, iota y of y, one of the sets the preimage of Q under H intersected with iota x of x, and the other intersection, which is the preimage under H of Q, but now intersected with iota y of y. So one of these sets must be infinite. Right, because well, my set P is the union of two sets. If I have infinitely many elements in the union, then it means that I have infinitely many elements in one of these two subsets. Okay, but this contradicts the assumption, which contradicts the assumption that both is important, both Jx, which by this universal property is equal to H composed of iota of x, and Jy, which again by the universal property is just H composed of iota of y, iota y, and this is x, are finite to one. You see, when I take the preimage of J of x of a certain element, and I have to look where the Q is. Okay, so so let's assume that I have infinitely many, and this ends the proof. I'm just trying to argue for this one last part. So to focus attention, let's assume that the preimage of Q under H intersected with iota of x is infinite. Okay, and now I'm looking at the preimage. So where is Jy? Yeah, jy ends up in Q, just as H, okay? So now I'm taking Jx, the preimage of Q. But this is precisely iota of X, preimage of H, preimage of Q. So you see, this is important that we have this assumption, because now I know that in the image of iota X, there are infinitely many elements from the preimage under H of Q. Okay. And when I take the preimage of infinitely many elements, then of course this is infinitely many elements. The preimages cannot identify points. Okay. The preimage of an infinite set is an infinite set. Okay. But this is important, that there are infinitely many elements in this set that are in the image of iota of X. Because this infinity would stick out beyond this image, when it wouldn't count. Okay, and of course, if the other set is infinite, not this one, then I just consider the preimage of jy, which also is supposed to be finite one, and this is how I get my contradiction. So this proves the lemma that indeed, under this assumption of one injectivity, I have my push-out in the category of sets and finite point maps. Any questions? Okay, so this is a very important lemma, because it adds to this previous lemma, which fixed the one color and vertex injectivity condition. So now we have a third condition, which let's call it one injectivity condition. Yeah, one of these maps should be injected. Okay. All right, but that's not everything. We have to prove another lemma. I was thinking very hard if it follows from the lemma already proved, about the contravariant factor of mapping into K and turning push-outs to pullbacks, if it's can be used to prove this lemma, but no, we just have to do it separately. And I think that in the remaining time, I will simply state this lemma. I don't know, let's see, maybe state, maybe prove it. Let's see how it goes. Right, so remember, we cannot now use this lemma of turning push-outs to pullbacks because we have a different functor. And it's not obvious that it happens, you have to verify. Okay, so let K be a non-empty set. With a distinguished element. Zero. And let F be an injective map. And also let this diagram, which we're drawing so many times over and over again, be a push-out diagram. In the category of sets. And finite to one maps. And it exists by the previous lemma, okay? So then I claim that I have what I want. Then all finitely supported maps from the push out. Sorry. Are equal to the fiber product. I find the supported sets from X to K. Cartesian product will find the supported sets from Y to K. And this is over finally supported maps from Z to K. Okay, so these are all maps, all pairs of maps to K, which agree over Z, so to speak. But it's given made precise by saying that a certain diagram is committed. Well, anyway, we know what the fiber product is, and here you go. So you have this equality, but of course, as before, you know that the push-out diagram is turned into a pullback diagram, okay, by the contravariant. So and the contravariant functor which is this restricted functor finally supported maps into K. This transforms the above push-out diagram into the pullback diagram. Where here I have finally supported maps on the push out. Here just pull back iota x and have finally supported functions on x. Here pull back iota y and you have finally supported maps on y. Okay, here you pull back, sorry, this is k. Here pull back f. Sorry, the wrong way. And you have finally supported maps on z. And here pull back g. To match finally supported maps on y into finally supported maps on z. Okay, so this is the pullback diagram, and this is in the category of sets and maps. Okay, this is a good time to stop, but I'm also very much tempted to prove it so that we are done with. Maybe let's have this additional 15 minutes and prove it so that we don't come back to it. But I have to improvise because I didn't manage to finish starting up the proof. So please bear with me if I get stuck. I hope not, but okay, so for starters, the above commutative diagram exists by the preceding lemma. Okay, so yes, that's right. I mean, map F is a functor in this category of sets and finite one maps, but I have to make sure that all the maps which I'm pullbacking are finite to one. But that's precisely what is afforded to us by the preceding lemma, right? Because F and G are finite to one by assumption, but we also assume that, say, F is injective to know that this is really a push out in my category where all maps are finite to one, and that IX and IY are finite to one. And when they are finite to one, yes, they do the maps, and of course they turn, this is a functor, so it turns commutative diagrams to commutative diagrams. But that doesn't prove it's a pullback diagram, okay? This only proves that there is a commutative diagram. And how do we prove that this is indeed a pullback diagram? Well, this is precisely how we did it with this previous lemma, where we didn't consider any restrictions and finite support. It works very much the same way, but there is one subtlety. I mean, half of it is identical and half of it is different. We have to go by the universal property, and we have to prove that this map witnessing universal properties is a bijection. And injectivity is basically for free. It works in exactly the same way, but the surjectivity requires a certain additional verification, which we didn't have to do before, okay? And then I guess that will be it. Okay, so what we're going to do now is to use the universal property, okay? So now we use the universal property of pullbacks. So because I have this diagram, oh, sorry, I did in reverse arrows. Sorry. I want here not Z, but I want the push out. Okay, iota X star. Well, this means that I have an object with two morphisms, which are then being equalized by F star and G star. So by the universal property of a pullback, there must be a map. And let me just denote this pullback by P. But we know that this is the fiber product. We're after all in the category of sets. And I'm just using the property that pullbacks in the category of sets and maps exist, and they're given as fiber products. So there exists this map H and maps going here and going there, right? Such that these two upper diagrams are also commutative. Okay, and these, how do we call these? Yeah, I guess these are called J's. Oh, wait a second, I did it in the wrong way, guys. Why didn't you correct me? Yeah. Sorry, this is yeah. But I'm it's It's nicer diagram if so this is up above. And here's my pullback. Okay, so here's my universal property map H. And here are my canonical projections, say pi x, pi x and pi y. And the diagram is commutative. So I have that I x pullback is equal to pi x composed with H, and IY pullback is equal to pi y composed with H. So that's what we have by the universal property in the category of sets and maps. Okay. Sorry, my handwriting degenerates places. So as I told you, the injectivity is proven in exactly the same way as we did it before, where there was no subscript f and no finite one maps assumed. So we take some map, say capital F, which is a map from the push out to K, say f and f prime. So let's take two elements here, f and f prime. And well, we wonder what happens when we apply iota x pullback to f and iota y pullback to f, and then we apply iota pullback x of f prime and iota pullback y of f prime. And they are equal. So we assume, so our standing assumption is that h of f is equal to h of f prime, okay? We want to prove injectivity. So now we want to prove that f is equal to f prime. But if h of f is equal to h of f prime, so I can plug in f prime to these two formulas, and I know that pi x of h of f is equal to pi x of h of f prime, but this is the same as having these two equalities, okay? But this two equality means that f composed with ix is equal to f prime composed with ix, and likewise f composed with iy is equal to f prime composed with iy. Sorry, this is iy, yes. But because the combination of images of ix and iy gives me the whole set, it means that f and f prime agree on the whole domain, so they agree. So this implies that f is equal to f prime. So we nowhere used any finite one. It's the identical argument as before. We just don't need it. This is well, who cares? Ix are finite to one, no problem. But it doesn't change a thing. To check injectivity, that's what we do. We have this map H, which we assume maps f and f prime to the same element in P. Then we use this universal property in the category of sets and maps, and we see that f must be equal to f prime. So no way out. This is simply an injective map. Okay. And there was absolutely no change because I didn't didn't care. I simply have my domain as these finally supported maps, and I have my IX pullbacks, IY pullbacks mapping to find supported maps, but that's irrelevant. It doesn't spoil a thing, because still we have these equalities which are encircled here. And we always have that Ix of X union Iy of Y is the whole push out. That doesn't change even if things are finite to 1. This is always the case. Okay, so now how about surjectivity? So hence H is injective. Okay. Now to prove the surjectivity, consider the diagram. And again, it will look like before, but there will be one additional thing to be verified. So I'm writing my push-out diagram, but I'm writing in such a way that I have a space for my set K, F, G, the push-out. Oh, sorry, the other way around. The push-out of X and Y over Z. Iota X, iota Y. Okay, so what is a general element in my pullback in my fiber product? You see here, I just wrote P, but I know what it is. P is the fiber product of these finitely supported maps over finitely supported maps. I know it because this is what the pullback is in the category of sets. Okay. So any element in this pullback will be just a pair of such maps which are compatible. Okay, so an element in P, I'll have, how do I denote these functions? Maybe F and G, okay? No, yeah, why not? F and G. So general element in P, this is a pair F and G. Where F is a map from X to K, and G is a map from Y to K. Right, let's make sure that we are doing it correctly. Yes, that's it. F is a map from X to K, G is a map from Y to K. They are finitely supported maps, that's by assumption. And they equalize, they have a commutative diagram, right? So F star pi X is the same as G star pi Y. So in other words, when I take F and G, F star of F is equal to G star of G. So F star of F is equal to G star of G, but it means that F composed with lowercase f is equal to G composed with lowercase g. But this means that I have a commutative diagram like this. I mean, going to the left, and then to K, and going to the right and then to K is the same thing. right? So now I claim I'm using the universal property of a push out. So now we can use the universal property of push outs. And this is of push outs, yes, in the category of sets. And this is important. And finite to one maps. Yeah, remember this is our assumption. You see, and let be a push-out diagram in the category of sets and finite to one maps. And because it's in this category, this universal property map H must be finite to one. This is essential. So why does this H exist? Well, this is just the universal property of a push-out, right? Because I have these two maps F and G that equalize lowercase f and lowercase g, so there must be a map H making these upper triangles commutative. Okay, so this exists, is unique, and is finite to one. That's what we were proving before. Remember? This is the preceding lemma. H is finite to one. Okay. So now, of course, we stipulate that an element. So I want to prove surjectivity. So I picked up a general element in P. And now I want to say that this is in the image of this map H. Okay. So now this pair FG is equal to what? I'm sure that it's something applies to H. This will be our map.
Sorry, I think you have too many H's there, right?
Oh, you're absolutely right, Niklas. Yes, you're absolutely right. Yeah, let's. How about the H tilde? Are you happy with H tilde? Yeah, you're absolutely right. This is a completely different H. This is the pullback H, and this one is the push out H. Thank you so much. Yes, of course. Yeah. So now this is with H tilde. Okay, but I still have to see what I'm doing here. Yeah, I want to prove that this H is surjective. Okay, but now, before I took this FF prime, but now I can take H here, right? Remember, I argued that by the previous lemma, this H tilde is finite to one. So it is an element of the set. Okay, it's a finite to one map from the push out to K. Well, in fact, we know more than just that it's finite to one. It has the desired property that the preimage of K less 0 is finite, right? Because this is what we mean by finitely supported. Okay, so let me see. Wait a second. So let me see. Why is it the case? I need more than finite to one. Sorry, we have to. So that's the additional thing that we have to verify. Finite to one is not good enough. Sorry. Now, I claim that the preimage, oops, the preimage under VH tilde of k less 0 is finite. Okay, and why is it the case? If I look back, sorry, I skipped the page. I know, but by assumption, sorry, G should have remained here. By assumption, F and G have this property. Okay, and I know. So okay, so let me write it down. I know that F preimage of k less 0 is finite, and the same is true for G. Sorry, this is G. And I have this equality. This diagram is commutative. So F is H tilde composed with IX. Okay. But F is H tilde composed with IX, and G is H tilde composed with IY. So the preimage of F is IX, preimage of under IX, preimage under H tilde. Okay. How should I do it? Okay, I should put this set here. K less 0. And again, we argue as before. We remember that IX X union IY Y is the whole disjoint union push out. Okay. So suppose the contrast. Suppose that this is infinite. Suppose that this is infinite. Okay. Then the intersection with either the image of I of X or the image of I of IY of Y is infinite. But then this set is infinite, which contradicts the assumption on F. Yeah. And if it happens that the other intersection is infinite, then F preimage, sorry, G preimage of K less 0 is now equal iota Y preimage of H tilde of K less 0. Okay, remember H tilde has a domain that disjoint union, but this disjoint, the pullback. But the pullback is the union of the images of iota X, iota Y. Okay. So one of these two sets, either this one or that one, must be infinite. But we assume that both F and G are finite sets. I mean that both F preimage of K less 0 and G preimage of K less 0 is finite. This is our assumption. Okay, so this proves, hence the claim is proved. Okay. And now with this, I can say, aha, H tilde is indeed an element of these finitely supported maps from the push out into K. Okay. And now I claim that H of H tilde is Fg. So the second claim is that this is right here. Now H of H tilde is Fg. And why is it the case? Well, just have to remember how H is defined. This is basically, how is it defined? Or do I use a commutativity? Yeah, I think we have equality if after we follow with pi x and pi y, we get the components. Yes, that's the property of the fiber product. Yeah, because pi x of h tilde, and now I use the commutativity of the diagram that pi x of h is ix pullback. And this is equal h tilde composed with ix. But now h tilde composed by x is f. And likewise, phi y of h tilde is equal iota y pullback of h tilde. This is h tilde composed with iota y, which is g. Okay. So things in the fiber product are equal if the projections on the direct on the Cartesian slots are equal, and they are by this computation. So hence, H is also surjective. And I guess it does the job because now we proved that that this unique map that you have by the universal property is an isomorphism. I mean, it's a bijection. This is the category of sets. There's a bijection which establishes all of this, and this means that you can think about these ix star and ry star after this identification as the canonical projections. So I think this ends the proof that indeed you have it. You have this, well, at least you have this equality for sure. Yeah, this is what we claimed here. So this has been proved now. What's the time? Oh my goodness! I went half an hour overboard. No, that's really the time to stop. I see. I thought it would be 15 minutes, and it was half an hour. Sorry about this. Yeah. Now, do we still need to do something to prove that this push-out diagram is turned into the pullback diagram? Well, the bottom part is no problem because it's the same thing. Now the question is to have to identify these pullbacks of ix, iota x, and iota y with the canonical surjections, but this is done by h, by the commutative diagram. Yes, so we are done. We are done. It proves that push out has been turned into pullback by this function. But you see, this was a little bit of fun. This was subtle. We had to prove that the h tilde, which we construct, which we have by universal property, is indeed an element of a set we want. Right? This was this argument over here. All that was non-existent before. So this is something that part was new. The rest was identical. Yeah. So what was new was this part. That's the most important page that allowed us to conclude the proof. Okay, so we meet at high noon in half an hour. I suppose I can stop recording, and we proved everything we wanted to prove for today. I'm very happy about it. And yeah, I stop recording and I see you in half an hour.